So, hello and welcome to the 41st session in the reading group, where today we're going to talk about an article called Using Machine Learning to Address AI Risk, which is written by Jessica Taylor from MIRI. So, this is Jessica Taylor, worked for MIRI in San Francisco as a research fellow. And this blog post that we're talking about is a written form of a talk she's given at the Effective Altruist Global Conference. And she is working at a subgroup in MIRI, which has the agenda called Alignment for Advanced Machine Learning Systems. And this article is a survey of the kind of technical problems that falls under this agenda. So the goal of this research agenda, in very general terms, is to make AI systems safe even at very high capability levels under a number of assumptions. And these assumptions are key to understanding this agenda. The first is that the current day AI research is generally on a track that will reach superintelligence. So it's the deep learning we're doing now will eventually result in a superintelligence, and it might do it relatively soon, meaning that we are talking in maybe a decade or two or something like this. The third is that it's possible to build a task AI, and that's a good idea and something we can learn from. And she talks a bit about these assumptions, in particular that these assumptions might not be true, it might not even be our best guess, but they are useful, because if it turns out that AGI is developed relatively soon, then this research will most likely be very valuable. If it's possible to say something about future AI systems under the assumption that they look like ours now, then that's an avenue of research that will be very valuable if it turns out to be true, even if it's not the most the likely. I'm hearing myself in the no problem. And I made a point here that this is called the streetlight effect. Some of you might have seen this cartoon before or heard about something similar, about a man dropping his wallet in the park, but searching for it under the light, because that's the only place he can find it. And Jessica Taylor, of course, is aware of this, and she argues that there is a chance that the wallet is where the light is, but this is something actually something I will get back to when I give my thoughts after this video. So, the first is, what is a task-directed AI? It's an agent that has a semi-concrete goal. Could be curing cancer, could be earning money, or doing charity, effective altruism, this kind of thing, but it's not this huge coherent extrapolated volition where we try to figure out what humans really want on reflection and doing that. And of course there's a particular task, she doesn't say it explicitly, but one particular task that we really would like this task AI to do is to solve the control problem. And that means if we start to build an AI, tell it how can we control you, the AI, and then after that, once we know how to control it, then hopefully we can bootstrap that into making AGIs with more far-reaching goals. And this a task AI should have humans in the loop, so to say, both in figuring out what to do, how to do it, and maybe even in doing the goal itself. And of course, the hope of this research is that this will not turn out to be really hard compared to building just a general AGI. In the last session, we talked about the model Racing to the Precipice, and from that model, there was a factor mu with how hard is it to do it safely compared to how hard is it to build a superintelligence unsafely, and that's the factor mu that we hope is high in this case. Now, there are 6 problems with this. that falls under this research agenda. The first problem is that actions are hard to evaluate. And of course, actions done by children can be evaluated reasonably easily. Problems, something done by your peer can be very hard to evaluate, and something done by someone who is strictly smarter than you can be really, really hard to evaluate. They can manipulate you, coerce you, cheat, or do covert actions or things like that, which once they are done by a super intelligence is really, really hard to fight against and prevent. Ideally, we want the AI to output an action saying, this is what I'll do, this task AGI, and give a proof or some kind of justification. And if the proof is too hard for us, then help us evaluate the proof. And of course, this can of course lead to infinite regress, where we hope it bottoms out in something we can really understand. But we hope that. This is something in computer science, something called the NP, the problems in the complexity class NP, which is something that has been studied very, very much. And in this case, it's something that Paul Cristiano has written about in an article called under the heading Informed Oversight. The second problem is test examples can be ambiguous. You imagine a human sees a lot of cats and figures out a generalization of what a cat is, and then when it gets to a new situation, humans generalize in a certain way, and it's by no means given that an artificial intelligence will do that. We want the AI instead to say if it is ambiguous, we want to say I am ambiguous. And this is in practice a real big problem for artificial intelligence as it is right now, because they are known to be extremely overconfident in practice. So if an AI is wrong, it usually says that it's very, very certain in its wrong conclusion. And this is called inductive ambiguity detection, and it's something that after presenting these 6 examples, Jessica Taylor goes a bit more into details about this. The third problem is that it's really difficult to imitate human behavior. Of course, many of you have heard about the Turing test, which is the problem where an AI is supposed to pretend it's a human, and there's a distinguisher, a judge, who needs to decide how humans behave and how AIs behave. And this becomes very, very difficult when the agent, the AI, is smarter than a distinguisher, because then the AI, the superintelligence, will in practice be able to do everything that the distinguisher cannot notice. This is also something Paul Cristiano has written about in Act-Based Agent and Mimicry and Meeting Halfway. The fourth problem is that specifying goals in the real world is really difficult. Like you would imagine, like make me a sandwich is a super simple goal. And even that turns out to be quite difficult, because with reinforcement learning there is a huge incentive to control the actual source of the reward, and there might be, in particular for superintelligence, a point in their capabilities where the incentives change. So they want to make a treacherous turn and control the reward button directly instead of the proxy that we are looking for. And this proxy can be really dangerous. Like if we don't specify make us a sandwich, but make sure there is that this camera is seeing a sandwich at a particular point, then this opens up a lot of dangerous opportunities for the AI to hack the reward. This problem is called the generalizable environmental goals problem under this research agenda. The fifth problem are the negative side effects. This guy here, it's the first time I see a picture of him, is called Steve Omohundro, and he theorized that a superintelligence will have a number of basic AI drives. It could be things like the AI is trying to make a sandwich and believes with 99% chance it can make a sandwich, but it also has to factor in the probability that a human will shut it down, maybe because the human doesn't want a sandwich. So the AI has an instrumental drive to stop the human from shutting it down. And there are 3 headings under which this research agenda tries to avoid these negative instrumental drives, called quantifying impact, mild optimization, and non-adversarial AI without instrumental pressures. The 6th is that there might be edge cases that still satisfy the goal. Bostrom has written about an AI that is told to make humans smile, and then it figures out that the edge case of making a tiny small smiling face, it satisfies this goal, and then it proceeds to tile the universe with small smiling faces. That's an edge case. And this kind of problem, if you go back to the sandwich problem, it might be possible to make a really small sandwich which counts as a sandwich. If it's measured by weight, we might have a huge sandwich. It might be a toxic sandwich. These kind of things that technically are satisfy the goal, but actually don't do it at all. In particular, there's a problem with adversarial examples, and I really love this example. Sorry, I can hear myself in one of you. If it's possible to mute. I think it might be you, Morten. There's some. If you could mute your microphone, please. It might be Victor who should mute his microphone. Yeah, I think it's fine now. Okay, so here we have an example, and I really love this example, where you have a image classifier which looks at the first image and says, I believe this is a panda. I am 57.7% confident that this is a panda. And then you add some completely random noise. It looks really like a random noise. If you ask the classifier what it is, it says, well, it might be a nematode, but it's totally unconfident. So this is just a completely silly picture. And you add it only with 0.07%. And then you get an image here, which is almost exactly the same as this panda. This panda is just to an extremely small extent distorted. To a human eye, these two look almost exactly the same. It's 0.7% of a change. But here, this example has been constructed so the image classifier now believes it's a gibbon, a completely different animal with 99.3% confidence. So this is a really dangerous case. It truly shows that it might be possible many of the AIs that we built right now are much more vulnerable to being cheated in this case by a smarter adversary than you'd think. No human would ever be cheated by this. No human would see a huge difference between this picture and this picture. But AIs, as we build them now, they do think that there's a huge difference between them. And the... Yes? Sure. The way I would see this, you have a plus between two images, and the question is, what does it mean to add two images? And what I imagine is that each pixel in the left corner has a red, green, and blue value, and in the middle picture, each pixel has a red, green, and blue value, and then you average these two, where you give this one the panda, the first, way more weight than the other, and then you distort this issue extremely slightly compared to this one, and then you get this this image. I believe that is how you add images. No. Yes. Okay. So We go back to the problem that was called inductive ambiguity identification, where the AI is uncertain and it needs to be able to tell us that it is uncertain. And maybe in practice it would be good if it checks with us. So if it's uncertain whether like a tiny smiling face should count as a human, if it's uncertain about this, it should ask us. And then we can say, no, it's not. You can see down here, there's a graph where there's a lot of positive examples in the upper left corner and a lot of negative examples in the lower right corner. And what's the difference between the two? There are a number of hypotheses, like everything to the right of this line is negative and everything to the left of this line is positive. But it could also be this line. We don't know which of these hypotheses are the truth. There's an algorithm called know what it knows learning, quick learning, and this outputs this ambiguity if it's more than a number of percentages uncertain about this, and you can make some assumptions. If you make a number of assumptions that are moderately reasonable, then this actually works out quite well. You need to have a number of hypotheses like these lines, and one of them needs to be true, and it needs to be a model with either a small finite number of dimensions or just a finite set of possible points. And under these circumstances, this really works. I took a picture here. This is Socrates, who knew that he did not know anything. That was I guess, his most famous sentence. And this is ideally what we want the AI to realize how much it doesn't know. And one of the ways that Jessica Taylor works on this is using a Bayesian view of the problem. And in this case, Bayesian statistics and predictions and probabilities. I've taken here a picture. This is Reverend Bayes, who invented Bayes' formula, and here you have an example of how the Bayesian update process works. You believe at first that the truth is all the way to the left. Here, that is your prior. And then you do some measurements, and the measurements are this blue here, you can see vaguely up here. That turns out to be what you measure. And then after this, your best guess at what the truth is this black line. This is your posterior. And in a similar way, you assume that there's some kind of true prior. Exactly what a true prior is a good question. It might be the prior that a superintelligence can find, and we have some kind of prior in our candidate AI, the AI that we are building, and we assume here, we make an assumption of how good the AI we are building is. We assume that it always finds a grain of truth. For instance, if k is 2, it means that the truth is that if our prior has a certain probability, then the true prior has at least half as much if k is 2. So this means that if we can make some kind of bound on how good our AI is compared to the truth, then it's possible to find some proofs and some algorithms to get very, very close to the truth, even if it might take somewhat longer. And that is what Jessica is working on. It should be said that there are 2 other agendas at MIRI, kind of at MIRI, 2 other AI safety agendas. The first is headed by Nate Suarez here, which is the Agents Foundation, which is much more about theory and the theory of reasoning and making decisions and proving that that programs satisfy particular properties, these kind of things. And on the other end of the spectrum, there are the concrete problems in AI safety, a paper that has been written by Dario Amodei and a number of others, which goes much closer to the current machine learning systems, and finds some things that can be problems and can be demonstrated in the current systems. And if a lot of progress is made of this, the hope is that this will be relevant to the big problems when you get an actual superintelligence. And this is only, I would say that Jessica Taylor is in the middle of these two. That these three agendas can be put on a spectrum, with Nate Suarez as the most long-term, and Dario Amodei as the most short-term, and Jessica Taylor somewhere in the middle. But that's just my understanding. She doesn't write this anywhere. Anyway, thank you for watching, and I'll stop the recording now.